And I'll leave the word to Carla for her introduction. Carla, the microphone.
Sorry, everybody, thank you for joining this meetup. I'm Carlo Orlandi from Larus, and I'd like to thank Simone and Gabriele for organizing this meetup and to hosting us. I'm glad to be here with Surya, Wing, and Jeff from Fujitsu Laboratories of America. They will talk us about how apply graph machine learning to chemical analysis and genomic medicine. And I go on without video to focus on the slide. I share my screen. Okay. Can you see my screen?
Yes.
Okay. I give an overview of graph technologies for for people who don't know. Graph technology, as the name suggests, organize that data in the form of graph based on the mathematical principle of graph theory. The real world is richly interconnected, and the graphs are all around us. Fundamentally, we can consider a graph as a collection of nodes and edges. Nodes typically represent entities. Edges are used to represent the relationship between those entities. The graph paradigm goes well beyond the graph database and application development. It's a new problem-solving framework that allow approaching the store, the analysis, and that visualization of data in an innovative way. We, Fujitsu Laboratories, we work with graph technology and graph AI application. And Jeff, Wing, and Surya can you explain what type of technology are. Biology, chemistry, pharmaceutical, and other life science work with interconnected information. Graph technology provides the capacity to model complexity, and we work with graph to find insights in connected data, such as various molecular systems, genome data, protein database, and drug interaction. In this slide, you can see two examples of graph representation to describe various molecular systems and protein interactions network. Graphs are foundational building blocks of next generation of machine learning. And thanks to partnership with Fujitsu Laboratories of America and Neo4j, Larus is able to provide to customer and end-to-end platform for machine learning. In a major advance to the field of graph AI technologies, Fujitsu developed Deep Tensor that use new tensor processing techniques and a deep neural network to automatically extract relevant features from a graph database. Larus, founded in 2004, Larus is the first partner in Italy of Fujitsu Laboratories and the first partner of Neo4j Graph Database. We are an Italian company focused on the development of analytics platform and AI application based on graph technologies. We are involved in some research projects and collateral trainings on SQL graph technologies topics with university and R&D department. If you are interested in learn more about Deep Tensor and Larus expertise, please keep in touch with me, with us, and follow us. Now I want to give the floor to my colleagues of Fujitsu, and thank you for your attention.
Hi, this is Jeff from Fujitsu. Thank you to Carla, and thank you to the organizers for this opportunity to speak with you. So I'm going to share my screen now. So hopefully you can see that. If not, please someone tell me. Anyway, so we're from my colleague Wing and I will present today. I will be going over a presentation, and then Wing will do a demo of our graphical UI and our machine learning. And you've probably heard of Fujitsu before. Fujitsu is an international technology conglomerate in everything from semiconductors, supercomputers, enterprise software, consulting. There's many things that Fujitsu does. Headquartered in Japan, but all over the world, and very strong in Europe. And we're part of, so Fujitsu has a research laboratory, and it does everything from kind of pure research in quantum computing to more applied research. And we're based in the Silicon Valley lab in California, and our particular group is focused on explainable graph AI. And to kind of start talking about machine learning and graphs, there's many kinds of machine learning you might do on a graph. And as Carla mentioned, when we're talking about a graph, we're talking about the kind of mathematical graph of nodes and edges. And so you can see here a couple kinds. So unsupervised learning. So this might be like clustering, where you have a bunch of samples of graphs, and you're going to put them into different groups that are basically the ones that are more similar or less similar, and you don't have any kind of labeling in advance. It's just, okay, I want to put it in a certain number of groups. Another kind of AI you might do with graphs is link prediction. So this might be something like I have a graph, and it is giving me, I have a new connection. I want to decide whether I should make that connection or not. Like
sorry, the slides are progressing actually.
What? They're not showing up?
No.
Yeah, the slides are not showing up, Jeff. Maybe
Yeah, I'm just seeing the title. Please.
Okay, because it says let me represent and try again. Okay. So you see that slide?
Yes, we can see it now, Jeff.
Okay, so
yes.
And if I move it, does that work?
Yes.
Okay, good.
Try putting in full screen, then we can test.
Okay, and now is it different?
Yes.
Okay, great. Okay, sorry.
It's actually a bug. It happens a lot of times.
Oh wow. Okay. Anyway, so I'm glad we got that resolved. So anyway, so link prediction is another kind of unsupervised machine learning, or you could actually be supervised in some cases, but you see that a lot in social networks. Classification is where you have a bunch of samples of graphs. So you have a lot of different subgraphs, and you want to put them into different groups. So like this is a network attack scenario, and I want to say where it represents normal traffic or an attack. So in this case, you need to have a ground truth because it's a kind of supervised learning. So you have a bunch of graphs you've already labeled, and then you're going to train a model based on that. And from there, you can use that on new data. And finally, regression in terms of graphs would be you have a bunch of subgraphs and you're going to assign a score to each one. And so you want to give it new graphs, then this is again a kind of supervised learning. So give it a new graph, then you will see if what you will predict what the score should be. So, and the score could mean anything like reactivity or, you know, your credit rating. And so Deep Tensor focuses on supervised learning. So we'll be focusing today on kind of classification and regression. Okay, and so why do you need special technology for doing deep learning on graphs? So most machine learning is done with that is done with neural networks. The neural network has a fixed architecture. So you have a fixed number of layers and a fixed number of inputs. And if you take something like image recognition or object recognition, any of that kind of computer vision applications, this is kind of a lot of work has gone in both in researchers and industry and kind of solving this problem. And what happens is typically you take a number of images and then you transform them or crop them to a fixed set of dimensions, a certain number of pixels, you know, width and height. And then that's easy to map to the inputs of the neural network. And then furthermore, there's convolutional stages that will pick out different parts of the image, and that makes it easy for the
sorry again, it's not moving again, I think.
You don't see the, okay. Did that change anything?
And
No.
Jeff.
Okay, so I can reshare.
Maybe try, as Wing is suggesting, not full screen.
Okay, I'm not full. Okay, I'll leave it as not. Okay, so we'll try one more time. Let's see here. So does that show up?
Yes.
Okay, so let's try this, and I'll say something like when I'm switching a slide, and if it doesn't show up, let me know, and then we'll try something. I mean, I guess the worst case, Wing has a copy of this slide deck, so we could present from his. Okay, so what I was getting at here is that so kind of image processing and deep learning are fairly well understood. Graph, doing machine learning on graphs is less well understood. There's a couple reasons for this. One is there's different ways to map a graph to a numeric representation that might be usable for inputting into a deep network. And for most of them, like this is showing an adjacency matrix here, the problem is that every subgraph may have a different size because you have a different number of nodes and edges. And furthermore, kind of it's very sensitive to how you did that mapping. And so, and there isn't something really that's kind of come out like a convolutional layer specifically for graphs that is kind of well-defined technology that'll kind of solve that problem. So this is a challenge. Okay, so I just changed slides. Did you see that?
No, Jeff.
Okay. Let's see. So I can reshare.
Jeff, do you happen to have multiple monitors?
No, not connected. No. So I mean, the other thing is I can try. I'm on Safari. I can connect on Chrome maybe, but there'll still be a little delay to do that.
That's, yeah.
Let's see here. Okay, so I will just real quickly present and represent every time. You see that now, right? Okay, sorry for the technical. So what I'm showing here, so this is our deep tensor technology developed at Fujitsu. And can you see that? Okay, hopefully.
Which slide?
It should show you, should say deep tensor technology at the top.
Oh, yes, yes.
Okay,
Yeah, it's done.
great. Okay, so, and what I'm just going to do is unshare and share every slide change. There won't be too many more. So anyway, the idea here is that to kind of deal with this kind of graph mapping problem, there's something called that's been introduced called a core tensor representation, and a tensor is a multi-dimensional matrix, and so it's using a technique called tensor decomposition to take the original graph data and convert it to a fixed size representation. And this mapping is initially done in a very trivial manner. And from there, then it's run everything. The inputs are mapped to a neural network, and it runs through the neural network. And you come back with classifications, and that results in errors when you're doing training. And so those errors are used in back propagation. This is a standard technique to refine the weights of this neural network. And then, but what Fujitsu has added is this step called extended back propagation, where it's fine tuning this graph representation. So the mapping or the tensor decomposition from the input graph to this core tensor graph is fine tuned and learned as you're going. And so it's basically finding the best representation to pull out the relevant parts of the data. And so that's dealing with that input mapping sensitivity problem I mentioned. So from there, then we can train and get classifications. And the other part of deep tensor that's interesting is it has explainability in the sense that it can output for each kind of basically for each graph that it classifies a weight on the nodes and edges that are explaining why it made a particular decision. So the nodes and edges that contributed more to the decision will have a higher weight than the nodes and edges that contributed less. And so then this can be used to help understand kind of this black box of the neural network and why it made a particular decision. Okay, so I will now unshare and share again real quickly. Actually, let's see here. Maybe we'll go on to. And so this is based out of one slide that I was going to show. I'll skip. This was based out of some research that appeared in the AAAI conference, one of the top AI conferences in 2018. So this is research done in our lab in Japan. Okay. So hopefully you can see this is the next slide is showing kind of a graph AI workflow. So just want to give you a sense of how you might use kind of graph AI in a larger project. So the idea is that you have some historical or known data that could be in a graph database. It could be in kind of various tabular forms as well. And then you're going to transform and sample this data to a smaller set and to a labeled subset. And then do kind of the machine learning development, which is sort of kind of set up, configure your system and set up hyperparameters, train it, test it, go back and forth until you're happy with your configuration, validate your final results. And then the output is a model. And then when you want to use this in production, what happens is you have newly arriving or unseen data, and you're going to transform it kind of in a similar way as you did here. And then you're going to apply your trained model to do classification or regression and get answers out. So that's kind of the workflow is pretty much similar to what you would do with a normal AI project. And kind of our focus in the demo you'll see today is more focused on this part here. Okay, so I will switch again. And okay, and so we have one of the things we've developed in our lab in Silicon Valley is something called Accessible Deep Tensor. And so this is a machine learning development workbench that kind of fills that development box specifically for graph AI. And so you can input data into the system, visualize it as in tabular form, map it to a graph, visualize the graphs and understand that, do sort of basically it'll do some auto ML and suggest values for hyperparameters, and you can configure it all you want. Then it runs training and validation, and finally visualizing explanations. And as its backend, it's using the Deep Tensor engine. So Wing will give you a demo of this in a few minutes. Okay. So this slide is showing some different application areas. Chemistry and genomics, which we're talking about today, cybersecurity. So this would be like network intrusion detection, finance, things like fraud detection, healthcare and human resources. So these may be, things like building knowledge graphs of health information or of employees. And I think they're doing some research in Japan on predicting when employees might take sick leave so they can kind of intervene sooner. So there's a number of different application areas for this kind of underlying technology. And let me... Okay. Sorry for the long transitions, but we'll work around this bug. Okay, so today we're going to talk about 3 specific use cases. One is bioactivity prediction in chemistry. Another is using knowledge graphs in genomics. And the third one is genomic research. So that again. Okay, so the bioactivity prediction in chemistry. So this was a use case using data from PubChem, and effectively there's different data sets there, but in this particular one, what they're doing is basically looking at a collection of related compounds and seeing whether or not a reaction occurs with a particular enzyme. And so this kind of thing obviously would have application because they're to get this data, the original data set, they're doing a lot of wet lab, chemistry to test experiments, to test the thing. So if you could predict which ones will react, obviously that would allow you to focus on those, or the ones that are more interesting versus the ones that that might be less interesting. So that could save a lot of human manual labor and time in the lab. So the way this is done is actually, it's pretty straightforward to model the elements of a compound as a graph. And so, the various atoms, and they're labeled with their, chemical symbol, whether, carbon or nitrogen or whatever, oxygen. And then the bonds between the elements are the edges in the graph. And so basically, we took all the data from one of these sets of experiments, one of these data sets, then use that as labeled data to train Deep Tensor and come up with results. So as you can see, this could be a very powerful application, and it doesn't need a lot of detailed information, to actually provide some value. Okay, let me discuss the next one. Okay, so the next one is about using a knowledge graph in genomic medicine. And so a knowledge graph is a graph where is representing kind of concepts and relationships between concepts. And you can typically, a lot of knowledge graphs are created through natural language processing, where you may extract, you have a set of texts and you're extracting information and building relationships automatically. And in this case, this was done at a teaching hospital in Japan. they took 180,000 genomic research publications and pulled out information from them. For example, this gene defect has these symptoms and can be treated by this drug. But you're getting information like that out and building a graph. And then they take this data and combine it with some patient data about their particular genome and genetic defects, and then train it to recognize, to basically diagnose a disease, and then using the explainability to provide the reasons of why the diagnosis occurred. Why, it was this publication. Basically, it comes out to be the citations. This publication says this, this, and this. And so this is a very powerful tool to provide, useful information to doctors. And because it has the explainability, you can kind of validate why it's making that diagnosis. Which, if it was a black box, personally, I'm not ready to trust a black box AI to my health. But for something like this, it can be, validated by humans, but save a lot of work. And so this is a very powerful application area as well. Okay. Okay, so the last one I'll talk about is genomic research. And this is a particular project that's in progress at the University of Tokyo, along with researchers from the Fujitsu Japan lab. And what this is about is there's modulators or control the strength of relationship between regulator and target compounds in various chemical reactions. And but in past kind of work, modulators were kind of looked at as the same for every person, but the effect of the modulator can be different for each individual. And so what was done is taking patient samples and modeling information from those as a graph, and then predicting the strength of the modulator based on that graph. And so from this, they're learning new genetic pathways and getting specific patient-specific information. Okay. Okay, so I'm going to finish the presentation part of this with kind of some comments on what makes a good graph AI project. So first thing is it needs to kind of be representable as a graph. So certain things like chemical structures, as you saw, it can be very easily represented as a graph. So that's great. And there's a lot of other things, relationships between people that can be represented as graphs. Also, relationships between concepts and facts, as we saw with knowledge graphs. That's another kind of area that's good for graph AI. And finally, there may be kind of data over multiple dimensions that doesn't fit into an actual relational model. For example, maybe multiple experiment runs or something like that, where they all kind of pertain to the same thing that you're trying to classify, but it doesn't fit neatly into kind of one row of data. So those are some areas, some kind of graph structures. But then the next thing is that the relationships that are there need to be obviously important to making the classification, because if not, then you might as well kind of use a simpler kind of machine learning. But there are a lot of problems where, as we saw with the three use cases here, or say in finance with fraud detection, where relationships between people and entities and businesses are important. So relationships are important to making the classification. And finally, you need to have a way to kind of divide up you might have like an overall graph, and you need to divide it into instances that can be easily labeled to create a ground truth for the problem for supervised learning. And so if you have all three of these areas, then it's a great area for graph AI. So I'm going to hand it over to Wing now, and I want to thank you and appreciate your interest, and we'd love to hear more about your kind of problems and that might be solvable with Graph AI. And we're partnered with Laris, as Carlo mentioned, and looking forward to work with you.
Okay.
Do you want to take all the eventual questions at the end? After?
Wing?
Can I add that we invite you to open experiment table with your companies and engage your data science team to validate deep tensor technology and explore find out the potential of your data.
Okay, I see Wing is. Can you hear us?
Yes, I can hear you. Can you see the screen?
Okay. Yes.
Okay, so let me know if thing doesn't move, and then we'll figure out how to deal with it. I hope this will actually work better than what Jeff is experiencing. So anyways, I'm going to run a live demo of accessible deep tensor on a data set that has been described by Jeff. This is a data set from the ChemPub data. And what we're trying to do is that this data set is kind of like showing the activity of a certain enzyme in the presence of different kind of chemical substances, okay? And you can see there are a lot of compounds that they've been examining in this data. There are like tens of thousands of them. For the quickness of the demo, I'm just going to pick like 100 of them and try to use machine learning to differentiate between the active one and the inactive ones. So if you go down, this is like the background of the data. So you'll see different kind of like molecule structures, and they will be showing that whether they are going to be active in making the enzyme work better or not. If you look at the last page, you'll see that. Okay, maybe something in the middle. It will show some inactive as well. So the Deep Tensor is a tool that is an interactive web app that allows us to take different graph data and run it through the Fujitsu Deep Tensor technology and produce predictions of the data. So on the left-hand side, you will see like the series of steps you have to go through. We have to like import the data and then represent the data in the graph, go through the machine learning, and also the last part will be visualization of the prediction. So I'll go through these steps one at a time, which is shown on the left-hand side. And the data set we're doing is the AID 778 demo. If I quickly look at that, as I mentioned, we have only selected like 96 compounds from like the tens of thousands of them. The data that is being represented is kind of like this. So every substance has a substance ID, and every row of the data is representing like a bond in the molecule. So in the bond, there are two atoms, and they are labeled with like certain number of numbers. So I mean, every atom will get a unique number, and then the type of element of the atom is represented as a per column. So S for sulfur, C is for carbon, so on and so forth. Okay. We incorporated this visualization tool called Google Facet so that anybody can actually look at the data and kind of feel the relation of things. So for example, you can see in this set of data, there are a number of, I mean, most of them are like carbon, and there are also different kinds of elements in the compound as well. And you can see about half of them, or maybe a little less than half, are like the substances that would make the enzyme not very active, and the other would be compounds that would make the enzyme more active, and we're trying to predict the value of them based on the molecular structure. So the first thing we have to do, we have to choose which columns we're using to build the graphs. And this one is pretty obvious. So we atom 1, atom 2. All the data they are labeled 0 are the compounds that will make the enzyme less active. And when they label 1, they are the one that made that more active. So I'm going to label them that way. And we also want to include the columns, which determine what kind of elements they are into our graph so that we can use it for the learning. So this will take a little bit. And in the meantime, this data is being now imported into Neo4j database, which we'll be using for the machine learning in the later phase. Okay, so because of the size is not that large, it kind of goes through pretty quickly. Okay, so now if you look at some of the graphs that have been created based on the molecular structure, you can see, I mean, obviously, like all the 6 ring of carbon are kind of like the benzene ring that's normally seen in organic compounds. And they're like these other elements, oxygen and so on, which are all going to be contributing the different way the data is going to be learned. For more complex graph structure, we'll usually have to call into the Neo4j database, which would be a much powerful visualization tool, because you can see up in the top, there are ways you can actually provide more query function, and you can kind of like limit what kind of elements you want to show in a particular graph. But for molecular structure, obviously these are simple enough that we don't have to go through some refinement of the query. And let me just show you another one here. So this is kind of a very simple looking molecule. So these are just a different type of molecular structure that we're going to use in learning. Okay, so now that all the data, all the different molecules are being represented as graph, we have to transform it into these tensor, which is the multidimensional arrays that we'll use to feed into the deep tensor technology. And we have a tool in here where will actually help you convert the graph into the tensor. And these are kind of like how deep tensor is going to put the different columns into the dimensions of the array. And once that step is done, we'll be almost ready to run the machine learning itself. So a few more parameters that we need to set. So among like the 100 graphs that we have in here, 80% of them will be used for training and 20% will be used for testing. And we have to control how many epochs you want to run it, which I set to 50 because it's actually a pretty fast learning in this case. So we'll set that up to get ready for the machine learning. Okay, so at this page, all the graphs has been transformed into tensor, and we're ready to run machine learning on them. So if I hit the run button, you will see the learning going on, and the learning converges relatively well. So hopefully I'll get some good results out of it. So after this is done, you'll get a confusion matrix about like how many true positive, which means like the prediction is hitting what the data base actually says. And Now I'll take the 20% of the test data and pass it to the model that was created by the training. And this step is usually relatively quick. And you can see I can get about a 78% accuracy in determining which kind of molecular structure of the substance are actually making the enzyme reaction more active or less active. Okay. We can run through the cross-validation step, but that's longer. And just usually we use that to validate whether they're like overfitting of the data. And in this case, I know it's not, so let's not waste that time and go straight to the explanation phase. So what the explanation phase does is that it will apply a technology called LIME and kind of like try to vary the input and kind of see whether the output by varying any of them would be causing like changes in the learning, and from there we can understand which part of the graph actually causes the learning result to happen. So once we're in the explain visualizer step, if I click on the graph, so these are like all the 12 or so results that we have in the testing phase just now. And you can see, obviously, there are a lot more true positive and true negative than the other, because we got like this almost 80% accuracy in the prediction. So if I click one of these molecules and kind of see what the molecular structure looks like, so you'll see like the nodes are either labeled red or blue. Okay, when they are labeled red, that just means that those particular edge or node of the graph is being considered by the tensor as main contributors for the prediction. So in this case, this is an active case, meaning this particular compound does make the enzyme activity go faster, and is picking out this particular atom in the structure, which happens to be a chlorine. So I guess based on the data set that we have, the presence of a particular element, chlorine, actually does help the reaction go faster. And we can look at a few others and kind of see whether there's any similarity. And sure enough, this is another compound that has the chlorine atom in it. And if you kind of look at the structure shown, this is not quite the same one. No, it's not this. But anyway, this is not the right database. Structure ID, that's the one I'm looking for. So you can see how the graph represent the chemical structure pretty closely, right? The two chlorine atoms, oxygen, sulfur, and all that. So, and obviously, if you want to see why there are some bad predictions that's going on, you can look at the graph as well. And you can see, even though this is like a false positive, meaning this compound should not be making the activity going faster, it finds really no good explanation in saying that this particular compound makes the activity go faster. So this is most likely a case of a false positive, and it says so properly. Any questions so far? Hello?
You can turn on your microphone for the questions if you want.
Hello? Yes?
Well, we'll wait until the end. I'll read the question from the chat so it stays in the recording. Okay. So
Okay.
Xavier is asking, how expensive is the process that recognizes graph elements?
Pardon? I did not.
How expensive is the process that recognizes graph elements? You can read the actual question in the chat if you want.
Expensive meaning?
Computationally.
Okay. So, I mean, I can talk about like the activity that's being run on the deep tensor. We do run it on like GPU in the background system. So for this particular case, it is a relatively small data set and it runs pretty fast. But for something like if there are like 10,000 graphs or so, and each graph size, if for example, there are about 100 nodes and edges, that usually would take about like 30 minutes to run. Are you looking for some more specific information?
No, just getting an idea. Thank you.
Okay. So usually, again, the training phase is going to be taking a lot longer time than the testing phase. So the number I gave you just now is probably about rough estimate for the testing phase.
But these core tensor elements that recognize patterns in the graph, they are specific for each run, each experiment, right?
So for each data set, you can run the training on a subset of it, and then you create the model, and then you can feed new data into the model and get the prediction. So if you change the set, I mean, if you have like new data coming in that you want to incorporate in the model, then in that case, you have to obviously do the training again. And then you will see how the added data would help improve or actually make the prediction worse. And obviously, usually in these cases, if you increase the size of the data, you normally get more accurate results.
So I actually have one question. So you see, I mean, there's a lot of graph framework, let's say, graph machine learning framework. Is this technology interoperable with some of them?
So
I'm thinking, for example, a deep graph library for graph deep learning.
So most of the graph learning, they'll have to map the graph structure into some other representation before they pass it into a neural network. And most of the thing we're seeing as comparison, they will map it to like a single vector. Okay. And the difference in the deep tensor technology is that we actually map into a multi-dimensional array, and that would actually make the training more accurate in our belief. And the other thing is that when Jeff was showing this slide about the extended back propagation, which is like the difference in the Fujitsu technology is that while the learning is going on, we actually do fine tune the conversion, the mapping of the graph structure into slightly different arrays, so that, I mean, different tensors, so that we can actually make the training more accurate. So that's a very unique feature that Fujitsu provides.
Okay.
Yes. The questions?
So if there are other questions, you can write them in the chat, or you can turn on the microphone. I guess we can take questions for all the speakers, right?
Yes. I can actually show you a little bit more. There's like a few more slides I want to go through.
Okay.
These are related to the genomic data set. So can you guys see it right now? Yes, so I'm going to show you some of the more complex graph that ends up in a kind of like a genomic data set that we also worked on. And it will take a longer time to run, so I'm not going to do it as a demo. But this is like a genomic data set that the University of Tokyo has been working on, as Jeff has mentioned. In this case, the graphs are a lot larger, and each graph is what they call a cell line. And the particular one that I'm showing in here is you can actually see that in the on the website. And within these cell line, there will be these genes which are either regulators or targets. So in one of these graphs, we'll have like 500 or so regulators and 1900 of targets. And this is a regression test case where basically every graph has a number attached to it, and the number that's attached to it is something called the enrichment score, which is kind of like shows how the genes are effective in expressing some cancer behavior. So this will be kind of like how one of these graphs will look like. And this is kind of like how these thousands of genes are being connected to each other in the explain graph. And if I just pick out all the nodes that have been colored, so I think these are like the particular genes and the relations that actually does contribute to the expression of the cancer behavior. And if I zoom in a little bit more, this is kind of how it looks like. So one way that we can look at the explain score is such that when we go through the prediction, we can basically quickly paste through all the different graphs and see whether like all the colored nodes are matching what is usually common between the different cases, and use it to predict whether I guess not to verify whether the predictions are acceptable or not. And sometimes if you go in and see some of these prediction explanation are actually not indicating what you expect, that usually means that you either might not have enough data, or you might have modeled the graph wrong, so that they are just different facets of the data that the machine learning is picking on, which is not representing the truth. And those are also all very important things, so that you cannot just use the AI as a black box. If you really want to make sure that the AI is doing the correct predictions for you, you actually have to look into this explained data a lot more to convince yourself that the AI is doing the right thing. Okay, that's all I got.
Sorry, just a question. Maybe I skipped this part, but is it possible to add dropout layer or regularization terms to contrast overfitting, for example?
To add what? Sorry, I didn't quite get the...
Sorry, no, I was saying, is it possible to contrast possible overfitting of the data through adding dropout layers or regularization terms like L1, L2? I don't know, maybe I skipped this part of the demo.
Hi, this is Jeff. So in the current design, it doesn't expose that functionality. All you can really control is sort of the number of layers and the size of each layer. I mean, that's something certainly that could be, it wouldn't be that hard to add something like that, but kind of the out of the box thing that Wing showed you doesn't have that functionality exposed. But you can control kind of how deep the network is and the width of each layer.
Okay, thank you very much.
Okay, we have another question in the chat. So they're asking, is transfer learning working for graph data?
Currently, this system does not support transfer learning, and I'm not aware of any work right now that does transfer learning for graphs. I mean, maybe I've missed it, but I haven't seen anything. You know, there's probably someone who's tried it, but I haven't seen any. Most projects that I've seen are focused on either graph embeddings, which you could look at deep tensor as a kind of graph embedding, or some kind of direct graph neural network. But I haven't seen research in transfer learning. I know, Wing, have you seen anything?
No, I'm not familiar with any of that going on.
Okay, are there other questions for all the speakers? So either Carla or Wing or Jeff? Again, feel free to turn on your microphone there. Okay, then I think we can, I'd like to thank all the speakers. Can I put my presentation? Wait. I just wanted to thank both Laros and Fujitsu for the participation and everyone who connected. Again, most people ask how they can follow us. I'd like to remind you that we are on Meetup, where you can find all our events, and we'll probably keep doing online events at the end of June and in July before the summer. And you can find us on Facebook, and you can find us on SlideShare and so on. And I'd also like to remember you that we're part of a larger no-profit association that is called the Italian Association for Machine Learning, which we use to promote quite a lot of meetups, and pretty much every meetup right now is focusing on online events. So there's really a lot of events you can choose from, and you can find us daily on Facebook, LinkedIn, Twitter. I mean, all the registration is free everywhere. And okay, so once again, thanks everyone for coming, and we'll send you the record. We'll upload the recording on YouTube as soon as possible. Thanks again to the speaker.
Thank you.
Thank you. Bye.
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 Thank you.
Bye-bye.
Yes, great talk. Thanks.